Okay, so let us continue. We will consider a few more properties of these asymptotic notations. So what do I mean by asymptotic notations? The notations that we have seen so far, big O, big omega, O, little omega, and theta. These are what are called asymptotic notations. Okay. So some more properties, and after that, this main lecture one, will be complete. Okay. So some more properties. So the first thing to note is that little o is in fact a stronger property than big O, and little omega is in fact a stronger property than big omega. Okay, so the first thing, that's what do I mean by that? So, okay, so let again f and g be functions from positive integers to positive reals. The first property is that if f is little o of g, then f is in fact big O of g. Okay. So how do we prove this? So let's look at a proof. Again, neatly in words, you should try to write it a little more carefully. I'll write it slightly in short. Okay. So since Fn is little o of Gn, what does this mean? We have limit n tending to infinity. So, or let me forget the limit. Let us write it in terms of the other equivalent form that we saw last time. We have for every epsilon greater than 0, there exists n naught positive integer such that f of n is less than or equal to epsilon times g of n for all n greater than or equal to n naught. So you see from here itself that we are actually getting fn is equal to big O g of n. Why is that? Because this is supposed to be true for every epsilon. For every epsilon, there is a choice n naught. So you make one choice of epsilon. So in particular, choose epsilon equal to 1. Then there is an n naught. Note that the n naught depends on the choice of the epsilon, right? So we chose epsilon equal to 1. According to that, there is an n naught positive integer such that f of n is less than or equal to 1 times g of n. So that is less than or equal to g of n for all n greater than or equal to n naught. And now that 1, the 1 that is here, that is the constant c that you're looking for in the big O notation, right? That is the constant c you're looking for in the big O notation. So this implies Fn is in fact big O Gn. Be a little careful when you want to distinguish between little O and big O. Okay. So big O, write it really big, and little O, write it really small, so that there is no confusion. Okay. So f of n is equal to little O g of n implies f of n is equal to big O g of n. In other words, little o is stronger. If you know it is little o, then it is big O. Big O is weaker. All right. Okay. So what is an analogous property? There should be an analogous property for the omega as well, right? So the second property is if f is little omega of g, then as you expect, f is in fact big omega of g. Okay. Very similar proof. Okay. Very similar proof. So I want you to try writing this down on your own. Okay, very similar and very easy. Just look at the previous proof and follow the definitions, you should be able to write this down. Okay, so this is the exercise, and we will discuss this when we meet next time. Okay, so if f is little omega of g, then f is big omega of g. In other words, little omega is stronger than big omega. Okay, big omega is a weaker condition. Okay, so that is what we have. The third property is in fact slightly more tricky. So the third property that we want to look at is it's in terms of limits. So this is one way of concluding that you can have f and g to be theta. Okay, so if there exists a lambda, a positive real number lambda, okay, not not any real number, but a positive real number lambda, such that limit n tending to infinity f of n by g of n is equal to lambda. Okay, so the limit fn by gn converges to a point that is positive, not zero, not infinity, positive number. Okay, then f is in fact theta of g. Okay, so this limit being converging to a positive number is stronger. Okay, f is in fact theta of g. All right, so let's prove this. How do we prove this? So we have lambda. So suppose there exists lambda greater than 0 such that limit n tending to infinity f of n by g of n is equal to lambda. Is that right? Okay. But what does that mean? This means for every epsilon greater than 0, just the definition of the limit, okay, nothing else. For every epsilon greater than 0, there is an n naught positive integer such that now it's a positive number. So it could be sometimes greater than the ratio fn by gn. It could be sometimes less than the ratio fn by gn. So we need to include the mod sign such that modulus fn by gn minus lambda is, we were using less than or equal to, so let's stick to that, less than or equal to epsilon for all n greater than or equal to n naught. This is what we have. But what does this give? Check. Okay. Now I'm writing this in short, but I want you to check this implication. Check that this actually tells us lambda minus epsilon less than or equal to f of n by g of n less than or equal to lambda plus epsilon for all n greater than or equal to n naught. Okay, check. This is very easy to check. Very, very easy to check. All right. So then what does this imply? Let's go to the next slide. This implies now g of n is positive number always. So multiplying by g of n throughout will not change the inequality. So lambda minus epsilon g of n less than or equal to f of n less than or equal to lambda plus epsilon times g of n for all n greater than or equal to n naught, right? So this is true for every epsilon. For every epsilon, we get an n naught such that this is true. Is that okay? So in particular, we have to choose some epsilon now. We have to make a choice. What is that choice? Well, in order to get theta, we require constants which are positive, right? This is already in the form that we require, but we need both of these to be positive, correct? But we know that lambda is positive. So make a choice of epsilon, which will make lambda minus epsilon also to be positive, but epsilon should also be positive. So the safest choice, there can be many choices. In fact, you can try other choices also. Safest choice is this: choose lambda is a fixed number, right? Lambda is the limit. Choose epsilon equal to lambda by 2. Since lambda is positive, epsilon is equal to lambda by 2 is also positive. Then what do we get? Then just by what we saw, there exists an n naught positive integer for this epsilon, for this choice, lambda by 2, such that the above inequality holds true. What is that above inequality? Lambda minus epsilon is lambda minus lambda by 2. So that is lambda by 2 times g of n less than or equal to f of n less than or equal to lambda plus epsilon is now lambda plus lambda by 2, that is 3 lambda by 2 times g of n for all n greater than or equal to n naught, right? And now are we done? We are done because we have an n naught and two positive constants c1, c2. So now c1, if you check, will be 3 lambda by 2. c2 is lambda by 2, both positive, such that this inequality holds. c2 g of n at most f of n at most c1 g of n for all n greater than or equal to n naught. So this is what it is, right? And therefore, by definition, this implies thus f of n is equal to theta g of n. Is that okay? So I will ask you to go back, rewind this video and go through this section once again, this proof once again, if something is not clear. We will discuss this anyways. You can ask me doubts when we meet, but just go through this part of the argument once again. Just rewind your video and go through this argument once again so that it is fully clear. Okay. Now I will conclude this part with a last comment. So remark, let me just conclude by saying converse is not true. The converse of this property is not true. Okay, I will stop at that and I want you to try and think about what do I mean by a converse to this statement. First of all, converse of which statement of this statement, property 3 that we just proved. Okay, this statement says if there is a lambda such that lambda positive such that limit n tending to infinity fn by gn is equal to lambda, then f is theta of g. I'm saying that the converse of this statement is not true. Okay, so I want you to try and understand what is first the converse of this statement. Think about it. What is the converse of this statement? And I claim that the converse is not true, which means you need an example which shows that the converse is not true. You need a counter example, right? So try to understand what the converse is. And since I'm saying that the converse is not true, try to find a counter example. Okay, so that is the last exercise that we have. So what is the converse statement? And what is the counter example? What is a counter example? There could be many. Just try and find one. Try and find one. What is a counter example? Okay, these two are also exercises. Okay, so we will stop this part here. So there have been a few exercises in the videos. Go through them, try and solve them, and we will meet and discuss your doubts and more about these things in the discussion session. I would also like you to tell me how things are going. If you're finding things to be fast or slow or whatever it is, let me know. Recorded videos will be slightly faster because you can always pause and think about it. Okay, so you don't have to keep the video playing. You can pause when something is not clear, think about it, and then play once again. That's why recorded videos will be slightly faster. But discussion session, again, we can slow down a little bit if you require. Okay, so that is the end of this video, and thanks for joining. We'll meet next time, as we said. Okay.